Hi, I'm David, and this is Maths Learning Centre seminar. Oops. Forgot to put the microphone on. Hi, I'm David, and this is the Maths Learning Centre seminar on the fundamentals, and this one's about rearranging equations, rearranging formulas and solving equations. So, I'm going to start with rearranging the most common kind of equation that's normally seen in physics and chemistry, and talk a little bit about rearranging other kinds of equations. But before I start with any of that, I would like to talk about the meaning of the equal sign. So what equals means? So if you look at an ordinary calculator, you'll see it has this button here that has an equal sign on it. And I have to say that's very misleading, because when we write maths on paper, the equal sign doesn't mean the same as what it means on a calculator. So on this calculator, if I do 2 plus 3 and I press the equal sign, what it does is it performs the calculation. I could do any number of strange calculations. And what the equal sign does is it performs the calculation. And that's true in a calculator, but it's not true in maths that's written on the page. Okay? It will be completely true if I write maths on the page. Let me just go back to something that's a little bit... It will be completely true if I write maths on the page like that. 2 plus 3 is equal to 5. That's completely true. But the equal sign doesn't really mean perform the calculation and produce an answer. What it really means is equal to. So when you read this aloud, it says is equal to 5. And this equal sign, just here, is read aloud as is equal to. And I can hear some of you saying, some of you listening, saying, David, that's stupid, that's obvious. Well, I want to make it even more obvious. This is declaring that 2 plus 3 is the same as 5. It is the same thing. Every time I see the number 5, I could replace it with the expression 2 plus 3, and it would be the same. And every time I see 2 plus 3, I can replace it with 5, and it would be the same. So it's declaring that they are the same thing in every possible circumstance. I can replace one with the other. So it's just as valid to say this. Okay, I don't have to have calculation equals answer. It could just as easily be 5 can be made as 2 plus 3 if you want to, but 5 is equal to 2 plus 3 no matter which way round it is. And I could just as easily write a statement like 6 plus 7, whatever that number is the same as 10 plus 3. They are the same number. The equal sign is saying that these two things, whatever they are the same. Okay, and that's a really big and important thing. Mathematicians are not really very interested in calculating to find out answers most of the time when they write on paper, and neither even are scientists. When they write a formula is not telling you how to calculate something, it's telling you the relationship between various numbers. Okay, so just to really ram this home, I could say, Superman is equal to Clark Kent. So in the famous superhero movies and television shows and comic books, Superman's alter ego is Clark Kent. I can say Superman is equal to Clark Kent. Not to say that there is a calculation, not to say that is Clark Kent that produces the answer Superman, not to say that there is a calculation Superman that produces the answer Clark Kent. It is just that they are the same person. So I can say that statement just as much as I could say any statement about numbers. The equal sign is just declaring a truth about numbers or about anything. That's what equals means. And I know I've spent like 5 minutes talking about that, but it's really, really important, and I will keep coming back to it. Okay. The next thing I want to talk about is what division means, and why the most famous basic formulas in chemistry, mainly, are related in the way that they are. Okay, so first I'm going to talk about what division means. So if I say 20 divided by 5, then that could mean a number of different things. It could mean 3 things. It could mean 20 objects split into 5 groups needs 4 objects per group. It could mean that. 20 divided by 5 could mean cut 20 into 5 pieces, and 4 is how much must be in each piece. So as a picture, it could mean 20 cut into 5 groups, and there's 4 per group. That's what 20 divided by 5 could mean. Okay. Or it could mean 20 objects cut into groups with 5 per group needs 4 groups. Okay? So 20 divided by 5 could be, the 5 could either be telling you how many groups there are, it could be telling you how many there are in each group. Like that. So they're the 2 things that it could mean, okay, in terms of a physical representation of what division means. And that's really important when you're trying to understand a formula, to think about what kind of division you're talking about. Okay, so if I'm going to look at those 2 pictures, they're quite different. One of them had 20 objects cut into 5 groups, and there's 4 per group. The other one had 20 objects cut into groups of size 5, and there's 4 groups in total. Right, that's important, and I will come back to that. So that means that 20, now let's go back a bit. If 20 divided by 5 could mean 20 into 5 groups with 4 per group, but that basically means that if I have 5 groups with 4 objects each, then there's 20 objects, which is a multiplication problem. 5 times 4 is 20. 5 lots of 4 is 20, which means that 20 divided by 5 is 4. So every time there's a division problem, there's a multiplication problem as well. So just, I'm going to go over that again. I might have to rewrite my notes later. So I'll just choose a slightly different example. 12 divided by 4 comes out to 3. And 12 divided by 3 comes out to 4, and 3 times 4 is equal to 12, they are all represented with the same picture. Three times 4 equals 12 could mean 3 groups of size 4 making up 12 objects in total. 3 times 4 equals 12. 12 divided by 3, well, 12 cut into 3 pieces leaves me with 4 per group, 4 per piece. 12 divided by 4 could be 12 divided into groups of size 4 gives me 3 groups. Okay, so we have 12 total. And I'll write it the other way around. 12 in total. Three groups, 4 per group. Okay, so that one picture can be represented with all 3 of those equations. 3 groups of 4 per group, 3 times 4 is 12. 12 total split into 4 per group is 3 groups. 12 total split into 3 groups is 4 per group. They're all the same picture. So what that means is that any formula that involves a division has 2 other formulas related to it that involve division and multiplication. So let me just give you an example of a formula that's got that in it. Just a second. One way that people write this to remind themselves that this is the way it works is they remember that mathematicians write division as fractions. And they say, well, just a second, 3 times 4 is the same as 12. And they like to draw this fancy triangle diagram like that. This is how some people remember it. So when we look at this, we have that 3 times 4 is 12. So if you cover up the 12, it gives you 3 times 4 is 12. If you cover up the 3, we get 12 divided by 4. So written as a fraction, 12 on 4 is 3. And 12 on 3 is 4. So I'm just going to draw the 3 pictures so that you can see it. That's 3 times 4 is 12. Or 12 is 3 times 4, either way. I could cross out the 4 and have 12 divided by 4 is equal to 3 is equal to 4. Or I could cross out the 3 and have 12 divided by 4 is equal to the 3. Okay, now this triangle only works for this specific mathematical relationship between division and multiplication. But that's what that triangles are trying to tell you, that any time there's a multiplication, there are 2 divisions. Anytime there's a division, there's another division and a multiplication. What that means is that when I see formulas like, what's a good one? Like density equals mass divided by volume, that formula there, well, if density is equal to mass divided by volume, we have this picture, right? We have this picture that there is a total mass and it's cut into pieces of size V. Just a second. Yep. And it, let me just think about this. Yeah, it's cut into V pieces. And the amount per piece is rho. I'll explain that in a second with actual numbers. But that's what it's saying. So it's saying that rho times V will be coming out to M because I have V pieces each of size rho, so V lots of rho is M. So all of these formulas are related to each other. So this formula also can be, or just as easily, that. They're all the same relationship between these three numbers. The mass and the volume and the density, those three numbers are related in this way. They are related by this division and multiplication idea. So an equation is not necessarily telling you how to calculate things, though it does tell you that. It's telling you how these numbers are related. Okay, so what that means is if I was told something like, let me just do that with actual numbers. The mass is 12 grams. The volume is 3 centimeters cubed. What is the density? Okay, so you can remember these formulas by remembering the per. Back when I did this, you'll notice that when I first talked about the division, I ended up with a per. I have 20 objects in 5 groups and 5 objects per group. Anything that has a per, because of that same idea, has to come about by a division. So when we think about grams per centimetres squared, centimetres cubed, that's saying I spread the mass across all of the centimetres cubed. So let me think about this. I have 12 grams in total, and it's made up of 3 centimetres cubed. There's one of the centimetres cubed, there's another centimetre cubed, there's another centimetre cubed. And density tells me, is saying, well, how much is there in every 1 centimetre cubed? So I go, well, these are my 12 grams, these are my 3 centimetres cubed, how much is there in 1? I should cut it into 3 pieces, and that will tell me how much there is per piece. So I've got 3 centimetres cubed, I want to know how much it is in 1, so if I cut it into 3 pieces, that'll give me 1 centimetre cubed bits, and so each bit will be 12 divided by 3. So I can go that the density Now, once you've been doing science for a long time, you just get used to the fact that per means division and you just go straight for it. Okay? But that's why per means division. And even if I was dividing it into, 3.8 grams per centimetres cubed, well, I'm dividing it into pieces. I've got 3 pieces of size 1 and then a little bit left over. And that's okay too. It will work with ordinary numbers, with all kinds of numbers, not just whole numbers. But I can just as easily go, the mass is 15 grams, the density is 3 grams per centimetre cubed. What is the volume? And here is where I can start using a formula approach rather than a picture approach, which is what your chemistry and physics lecturers, that's how their brains are set up, because they've spent years practicing thinking in formulas. So they will go, oh, well, just a second. They will go density equals mass divided by volume. And so when I think of my little triangle, the density is the mass over the volume. I could just as easily go, just a second, volume would just as easily be mass divided by density. According to that relationship. So the volume must be 15 over 3, which is 5 centimetres cubed. Right, so that is the philosophy of that particular kind of rearranging of formulas. Now there are some maths educators who hate this triangle diagram with all the fires of hell. And the reason it is because it only works in this situation. If you have a simple formula that involves one thing divided by another thing, you can rearrange it using the triangle. But other formulas it doesn't work for. Okay, it only works in that situation. And the reason it works in that situation is it's just a fundamental understanding of what multiplication and division are. So just be aware that you can't rearrange any other formulas than these three kinds using that information. Or you can wiggle it a little bit, but there are times when it will just fail dismally. So when I actually think about density and molarity and all of those things in chemistry and speed in physics, I actually literally draw that picture of cutting things into pieces because it helps me remember what's really going on. Chemistry works particularly well because in chemistry you really are slicing things into smaller pieces. That's because you've got an object and it's cut into smaller bits. Whereas physics is a little bit more esoteric than that. So that's the first kind of formula. And now I'm going to get on to basically any other kind of formula. So I should say that an equation is any statement that has an equal sign in it. And an equal sign, so, you know, an equation is a statement, you know. With an equal sign in it. And when I say statement, I literally mean it in the grammar sense. It is a sentence that has equals in it. Okay? Exactly as I said right at the beginning, you know, Superman is equal to Clark Kent. Perfectly good statement that has an equal sign in it. That's an equation. Normally an equation has math stuff in it though, right? So a formula, on the other hand, is a particular kind of equation that has single concept equals something else. So a formula will always be and the other stuff might be quite complicated, but that's what a formula is. And that thing is a single letter usually. So when in a formula like rho equals m on v, that's a formula. It's a perfectly good equation, but it's a formula because it's single letter equals. And the reason it's called a formula is because it allows you to calculate something. Whereas an equation may not let you calculate anything, it may just tell you information. Okay, so in a pure sense, solving an equation means rewriting it as a formula. Okay? Right. So this works best with examples, but I just wanted to point out the difference between an equation and a formula in case you were wondering. Right. So an equation is a statement with an equals, and it doesn't have to have unknowns in it. 2 plus 3 equals 5 is a perfectly good equation, but often the equation will look something like 2 plus x equals 5. That's a perfectly good equation. It tells me that there is some number x, I don't know what x is, but whatever x is, 2 plus x is the same as 5. The number 2 plus x, whatever that works out to be, is the same number as 5. And usually the goal of this is to figure out what x is equal to. So in any equation, your goal is normally to get to this stage, to keep writing new things that you know to be true. You're going to start with an equation, you're going to write another equation that you know is true, and another equation that you know is true, and another equation that you know is true, until you get to an equation that looks like this, and that will tell you what x is. Okay? So with this one, you can just stare at it and go, well, 2 plus x is 5. Well, the only number I know that adds to 2 to give 5 is 3. Okay? So this is called solving an equation. You don't have to do any working in between them. You're allowed to just write down the next one. So I'm saying that, look, 2 plus x is 5 is a perfectly true, excellent true statement. X equals 3 is another true statement which happens to tell me what x actually is. Right. But it's never nearly as simple as 2 plus x equals 5. They may be more complicated than that. So one of the ways that we think about equations is thinking about the number x and thinking about what stuff has been done to it. It might be an x, it might be a t, it might be a v, doesn't matter. We think about what stuff has been done to it in order to produce another number which is the same. So I'm going to show you how to solve what looks like an extremely complicated equation. Now I won't call it W, I will call it P, for reasons that will become clear shortly. Just give me a second, I'll try and think of what P is. There we go. Okay, so this is my equation. So it tells me that whatever the number p is, p plus 3, then times 7, then plus 2, divided by 8, and then plus 6, is the same as the number 5, 15. So anytime I saw the number 15, I could just as easily replace it with that. I wouldn't, because that would be stupid, but yeah, I could. It's declaring that whatever whatever the left-hand side is the same as whatever the right-hand side is. One is Superman, the other one is Clark Kent. I'm presuming that this is Clark Kent. This is Superman because he doesn't look like Clark Kent because he's been dressed up differently. Okay, so I need to try and figure out what's going on there. And I'm going to think what has been done to the number p. If I started with the number p, if I think carefully about the order that operations have to be done in, the BODMAS that people would call it in school, but just the order of operations, the order of operations says that I should start with the brackets first, right? So I should do the plus 3 first, and then times comes after, is the next thing you should do, times, because times has to come before plus. So I'll do that. I'm supposed to do bits on the top and bottom of fractions before I do anything else, so I have to do that bit first, which means that the 8 is next, and then the 6 is next because it's a plus, and you always do plus last. So that's the order I did it in. So let me just draw a picture of what just happened there. I had p, and then I plus 3, and then I times 7, and then I plus 2, and then I divided by 8, and then I plus 6, and once I did all of that, the result was 15. So it seems reasonable, if I wanted to know what p is, I should do those backwards. So instead of adding 6, I should take 6 away. And instead of dividing by 8, I should multiply by 8. And instead of adding 2, I should take 2 away. And instead of timesing by 7, I should divide by 7. Instead of adding 3, I should subtract 3. And that should tell me what p is. Because remember that this equation is not really telling me how to calculate p, calculate the number 15. It's telling me how the number 15 and the number p are related to each other. P and 15 are related by this sequence of events. And so if I do the opposite sequence of events, that should tell me how 15 is related to p. I'm going to do an illustration of that, as is my wont, in order to make my point. So what I did is I took my number p, let's say it's this calculator, and I added 3 to it. And then after I added the 3, I multiplied by 7. And then after I multiplied by 7, I added 2. And then after I added 2, I divided by 8. And then after I divided by 8, I added 6. And when I did that, this object is the number 15. So in order to get back to the p, which is right in the middle, I'm going to have to remove them in the reverse order. Instead of adding 6, I'm going to have to do the opposite of adding 6, which is subtracting 6. Instead of dividing by 8, I'm going to have to do the opposite of that, which is timesing by 8. Instead of adding 2, I'm going to have to do the opposite of that, which is subtracting 2. Instead of timesing by 7, I'm going to have to do the opposite of that, which is dividing by 7. And instead of adding 3, I'm going to have to do the opposite of that, which is subtracting 3, and that will give me the thing that I started with. So one of my people who taught me how to teach high school maths called this pass the parcel. If you've ever played a children's game called Pass the Parcel, where there's a prize in the middle and there's all these layers and you pass it round, and when the music stops, someone takes off a layer, and then you've got to keep taking off the layers until you get to the middle. So I call this unwrapping. Okay? So I'm going to have to do these things. So if I start with 15 and in turn do minus 6, and then after I've calculated that times 8, and then after I've calculated that minus 2, and then after I've calculated that minus 7, and then so divide by 7, and then after I've calculated that minus 3, it should tell me what p is. Okay, and that's great. You know, I could just get my calculator and actually do that calculation now. So 15 minus 6 gives me 9. 9 times 8 gives me 72. 72 minus 2 gives me 70. 70 divided by 7 gives me 10. 10 minus 3 gives me 7. So p must be 7. Let's just check that. If I started with 7 and did plus 3 and times 7 and plus 2, and then divided all that by 8, and then plus 6, I get 15, exactly as I should. Okay, that is the magic of unwrapping. But this doesn't look particularly mathematical. You know, if you put this in your assignment, they'd go, "What are you doing?" And so I can show you the other way of thinking about this that mathematicians use, which is a very flexible way of thinking and is useful for solving all sorts of equations and not just this kind of equation. And it hinges upon the fact that you can rearrange things in different ways. And it hinges upon this very idea. So let me start with the same equation. So what I can do is I can say, well, which bits have been glued together by doing stuff? You know, the last thing that was done is this plus 6. All of this is stronger than the plus 6 in the order of operations. Division is stronger, that glues things together. So I have all of this stuff, whatever that is, plus 6 is 15. And so that number would have to be 9, because 9 plus 6 is 15. So I can imagine just unwrapping the first layer and saying something plus 6 is 15, so that something must be 15 minus 6. Okay? Right. So I can write that down. My something was p plus 3 times 7 plus 2 over 8. Must be the same as 15 minus 6. And 15 minus 6 comes out to, is the same as 9. Okay? Right. So this thing is equal to 15 minus 6, but 15 minus 6 is the same as 9. And then I can do it again. Now I can say, just a second, all of this got divided by 8 to produce the number 9. So, just a second, if I divide it by 8 to produce the number 9, I should times by 8 to do this backwards. And 9 plus 8 times 8 is 72. And then let's look again. Oh, interesting. That object plus 2 comes out to 72. So whatever that object is, it must be 72 minus 2. And now we have this object times 7 is equal to 70. So in order to reclaim this object, I have to unwrap the times 7, which means I have to divide by 7. And now finally, I'm down to the object I was looking for. P plus 3 is 10. So to unwrap the plus 3, I'm going to have to subtract a 3. So I've now figured out that P is in fact 7. And that is how people unwrap equations. Unfortunately, when people write these things in their working in lectures, they will often not do some of the steps, and they'll do it direct. And unfortunately, again, there is yet another way of thinking about this, which is even more flexible. And I'm going to show you that in the last few minutes. However, the ideas about how to go about solving the equation are the same. What you need to do in all of these is investigate what was done first so that you can remove it. Let's do this one more time. And I'm going to really use the philosophy of what equals means. All right, I'm going to really use what equals means. This number and this number are the same number. That's what the equal sign means. Okay, this is Superman, this is Clark Kent. They are the same person. So therefore, if I do the same thing to them, they will still be the same. Okay, so this is the number 15. If I add 1 to it, it will be the same as if I added 1 to this, because this is also the number 15. I could times it by 8, I could divide it by 250, I could do whatever I wanted. As long as I did it to both, then they would still be the same. And the equal sign is designed to say that things are the same. And remember, when I wrote this equation before, this working before, I wrote a whole lot of statements that all had equal signs in them. I used the one I had to make a new statement about a new object, and this object is equal to 9. That one's equal to 15, but this one's equal to 9. This one's equal to 9, but this one's equal to 72. This one's 72, but this one's 70, until I could get down to make a statement about the number p, which is what I was aiming for. I'm going to do the same trick, but in an ever so slightly different way. It will feel different, but it will look very, very much the same. So let's think about this. I'm going to think about it in exactly the same way. I'm going to say, see this number here, if I subtract 6 from it, then this plus 6 will go away. Exactly as what I was doing before, right? I've wrapped a number up by by wrapping it up in a plus 6. Okay? I've got my last layer of the parcel is a plus 6, so I need to subtract the 6. But instead of thinking of it as subtracting the 6 from the 15, I'm going to subtract the 6 from both. Okay? I'm going to say all of this Okay, I've just rewritten what I just had. P plus 3 times 7 plus 2 over 8 plus 6 is equal to 15. Now those two numbers are the same, so I could very, very easily just do whatever I wanted to both of them, and I will subtract 6 from both. And here is where the power of rearranging formulas. Just a second. Plus 6 and a minus 6. There's no reason I have to do this first. I could just as easily go plus 6 minus 6, which would give me 0, which means that I end up with and 15 minus 6, well, that's the same as 9. So you'll see that there is only one difference between what I have here and what I had on the previous page. In this one, it's almost as if the 6 moved to the other side. In this one, I literally wrote a minus 6 on both sides. And most people find that the most effective way of solving equations. I'm looking at this and I'm seeing this object divided by 8 is 9. So if I take the entire of what I've got, copy it down exactly as it is, and do this, then over this side I'm thinking, just a second, number divided by 8 times 8, that's the same as not doing anything. And 9 times 8 is 72. I could do it again, copy down exactly what I've got because I'm going to change it, but I have to change the both in the same way. Call that plus 2, it's sitting out there all on its own, so it's ripe for subtracting a 2. And the plus 2 and minus 2, they, you know, plusing 2 and minusing 2 is the same as not doing anything. I can copy exactly what I have here and divide them both by 7. Oh, timesing by 7 and dividing by 7, that's the same as not doing anything. And again, one final step. I could subtract 3. Plusing 3 and subtracting 3 is the same as not doing anything. This is what your lecturer's working would be more like, except they would have skipped every second step. They probably wouldn't have shown that step. They wouldn't have shown that step. They wouldn't have shown that step or that step or that step or that step. But I find that it does help me to keep focused, to just copy down whatever's there and do the opposite of the last thing that was done. So I'm going to do a brand new one so that you can see how it's done. All right. The key to this is knowing what the opposite of things is as well. So let's see. This is probably going to give me an awful answer, but I'm just going to continue down this road. Okay, this equation is slightly different because it has some extra symbols in it that aren't involved with the x. So the first thing I'm going to do is work out as much as I can. Okay, so look at this. The 8 times 3, I can figure out that. That's supposed to be done first. I can figure out what that is before I do anything else. And the 4 plus 1, well, that'll come out to 5. And because it's all grouped under the bottom of a fraction, I'm supposed to do it first anyway. So the first step in any of these things where you have to solve equations is actually to try and figure out what everything else is so it's not so confusing anymore. Okay, so now let's investigate. What has been done to my x? If I start at the x and work my way out, I had to add the 5, and then times 7, and then add 24, and then divide by 5, and then add 3, and it came to 18. Cool. So I need to do those things backwards. The last thing that was done was the 3. I'm going to have to remove that plus 3. So I will write down exactly what I have, and I will take 3 from both of them because they are the same, and if I take 3 from both of them, they're still the same. But plus 3 and minus 3, they don't really do anything if you do them both. And 18 minus 3 is 15. So now let's have a look. What's the last thing that was done? X plus 5. The last thing was to divide by 5. So I need to get rid of that now. Because just like my pass the parcel, the last wrapper that went on has to come off first. So I'll copy exactly what I have, and I have to get rid of the 5. So I have to times by 5 because it's currently being divided. So dividing by 5 and then timesing by 5, that doesn't really do anything. So they're going to disappear. And 15 by 5, that's the same as something. 75, I think. I'm just going to check that one. Yep. And then let's have a look. The furthest thing from the x is the 24, so I'll deal with that next. Copy down exactly what I've got. I want to remove the 24. It's currently being added, so I will subtract instead. So 24 minus 24 comes out to plus 24 minus 24 comes out to not doing anything. 75 minus 24 would be 51, which is horrifyingly not a multiple of 7, but that's okay. It's all going to be nice fractions from now on. So on to the next page. The next thing that needs to be removed is this 7. It's furthest from the x. So timesing by 7 is the opposite of dividing by 7, so I'll do that, and that will make the times 7 go away, because times 7 divided by 7 is the same as not doing anything. And whatever 51 divided by 7 is. I don't think it's a multiple of 7. Maybe it is. No. Yeah, because it's 17 times 3. That's where the 7 was. I knew that there was a 7 there somewhere. 51 is the number of Jenga blocks in a Jenga set. And Jenga set has 17 layers and 3 blocks per layer. I'll just leave it as a fraction for the moment. And then the last thing, the plus 5 needs to go away. So I will subtract it. And that will require me to figure out what that is. And I could use a calculator at this stage if I wanted, or I could start doing fractions if I felt like the answer should be a fraction. So in maths, the answer would be a fraction. In science, the answer would probably be rounded off to a couple of decimal places. So whichever seems appropriate in the context that you're working in. So in science, I'd actually just go 51 divided by 7, and then take 5, which gives me 2.2. to 4 decimal places. That would be in science. Or I would have to put it all over a common denominator, which is not fun. They need to have 7s on the bottom and able to subtract them, because you're not allowed to subtract fractions unless the bottoms are the same. So I could do this 5 as a times 7 and divided by 7 like that, so that it has a 7 on the bottom. And 51 minus 35, 40 minus 35 would be 5, so it must be 16 then. Let me just check if I've got the same answer, hey? Yes, okay. So if you're in maths, you'd leave it as a fraction. If you're in science, you'd do it as decimal, depending on what you're aiming to achieve, of course. So that is not all there is to solving equations. There are plenty of other kinds of equations. In particular, logs and exponentials are particular kinds of equations, and that's what next week's seminar is about. And there are quadratic equations too, so I may be able to fit quadratics into the next week's as well. I'll see how I go. Yes, but in general, if you can investigate what has been done to your missing number, you can unwrap those things that have been done to figure out what the number is. And all other equations, the goal is to turn it into something that you can unwrap in that way. So all equations, the goal is to get down to an x equals or a t equals or a w equals or whatever it is. But equations that don't look like a pass the parcel, if you can turn them by some methodology into something that is a pass the parcel, then you can do it from there. And that's the philosophy. And I will continue on that next week. Yeah. Cool. But I have to stop now.